Thank you for joining today's glTF meetup. Joining us today are Thomas Stockhammer and Imed Bouazizi from Qualcomm. First, a couple of housekeeping items. If you have any questions during the presentation, please ask them using the Q&A feature located on your Zoom toolbar at the bottom of your screen. We are recording this webinar and we'll show the link to the recording along with the slides on the event's webpage. At the end of the session, please complete the short survey to help us better design future events. On today's agenda, Thomas and Imed will describe glTF 2.0 extensions in MPEG and 3GPP. Thomas, go ahead and take the screen and let's get this started.
My camera is on now. Thank you so much, Jeff, for the introduction. Thank you to Kronos for inviting us. This is kind of a nice wrap up to coordination we had over the last couple of months, actually years. And the title was introduced already. And so we have been giving a bit of an overview of this together with Imed. So let me move forward. So on the agenda, we give you a bit of background on the use cases and the solutions. Then we have looking at considerations, what is needed for an immersive exchange format. We're going to be looking at MPEG immersive architectures, MPEG extensions to glTF 2.0 would exist. There will be a demo and an outlook into the future. So just, I'm not going to go into the details of the presenters, you see it here, but just as a background, I'm leading the working group in MPEG that has developed the MPEG IC description with the extensions here, active in 3GP, and Imed is the chief editor of the standard that we're going to present later, but also has different roles in different organizations to support XR experience. So let's dive into this a bit. And we started with a couple of selected use cases designed for portable dynamic 3D scenes. That's what we're referring to. And this is a bit inspired by a group which is 3GP, so the group that looks at mobile networks and mobile delivery of different types of experiences. But it's not limited to this, we just use it because it's kind of motivating some of the standardization work. A first use case is actually something that is very broadly as accessing dynamic and interactive 3D scenes, and you can consume those probably in the context of an AR, MR, or VR environment. So, and there's obviously different use cases depending on your device, your environment, and so on. And there is many examples what you could imagine, and we don't want to go into details that have been discussed, from live entertainment concerts that are streamed or distributed in 3D, movies in 3D, where you can interact, games or other type of environments. And typically these type of use cases is a collection of static and dynamic objects. They need to be presented jointly and basically also accessed and downloaded from some network service environment. Huge volumes and data sizes to be expected, stressing the network and making it complex to get into devices. There are typically interactive and immersive, so there's different of natural interaction by your body movement, interactions with hands and controllers, and you get different media types. It's not just visual, you have audio, you have haptical aspects and so on. And the access happens through downloading this, but downloading assets is a huge stress. So preferably you do some kind of smart streaming that allows you to basically leverage what you get on your network bandwidth. And at the same time, you need to adapt to very different device capabilities. You might have devices such as desktop computers that are obviously very powerful to devices that are very limited in the capability, but still want to experience this. And we have a bit more on this later because that's driving some of the design criteria as well. So there's another use case, and what I did now is basically just enabling this one. Okay, I'm going forward. And that comes also out of 3GP. It's about using 3D and AR call and conferencing. And basically, this is existing today. The conferencing is a core aspect about a mobile communication system. But what you would like to do is having multi-party calls and conferencing that integrates AR, to some extent avatars, making it basically much more a virtual scene. And you can join with realistic avatars and contribute to 2D and 3D content. So creating the shared spaces where a call and the participants can interact and collaborate. So That's a great vision, but basically also a great use case to look at different of aspects that are needed to getting this done. This is just a high-level procedure. You're giving an idea, and what you're basically doing is you're sharing scenes, and basically the scenes are shared across different participants, and you have a single central rendering engine, a game engine, a computer that creates the scene, and you basically are added to the scene and the nodes, and then these scenes are dynamically updated. So new users might be coming in, you adding new objects and so on, but you can interact with your pose, your animation, your triggers into the scene, and then basically the scenes are again sent and updated. So you basically need an exchange format to dynamically describe the scenes, to contribute to the scene, to aggregate different objects. So that's one of these basically use cases that shows that scene exchange is an important topic. So now that gets a bit busy. What we did in 3GPP, and 3GPP is just a placeholder for a mobile industry. So we have a reference architecture for a device that is basically an XR. And that could be something like a glass like this. So very limited in terms of what you can do in terms of processing potentially, limited in power consumption, limited in battery consumption, processing, limited in weight, and so on and so on. So what you basically still want to have, you want to access this with scenes, richer scenes, lightweight, and there are also different type of devices. So we have been broken down a device like this into different aspects. And one is accessing the content, going over physical layer system, and accessing through different assets where you need, for example, compression formats, representation formats for different media types. And then you basically go into something that is the core of where Kronos is working. You try to basically present this data through basically a scene and through rendering. And then you go into basically a runtime that adapts the scene to the device functionalities. And basically a core aspect what we identified is to have interoperable formats in this environment that supports basically content providers and application providers to run scenes against these type of devices. Now, and obviously looking much more also into the future when these devices get more prominent. So requirements for doing this include actually different capabilities to be specified, but one of those is a scene description that basically allows to describe the workflows. I come back to this a bit later. And there's additional work happening in 3GP to complete this framework, but the core aspect is basically aggregation of scenes and describing this properly. Another aspect that is also in the context of what you have seen before, in order to enable rich user experiences on lighter weight devices such as glasses and so on, one approach is, and that is very prominently researched and implemented, is what is referred to as split rendering, meaning you run basically your application, the game engine, on the server, and then you basically prepare or pre-bake your scenes in a way that the device, according to its capabilities, is able to render this. In a simple way, you would just use maybe a runtime to do some post-processing, but you can also split the distribute, and you basically are also operating then in some latency environments and constraints that are restrictive because of your interaction with the scene and your body movement and your immersiveness. Also, but this is identified that we basically need to be able to set up rendering split flows, that we need an entry format that describes the scenes and that basically exchange of capabilities and scene objects and the description, for example, of these rendered frames can be properly done. So all of these are selected use cases that motivate that we need exchange formats, and these exchange formats are then aggregated into certain contexts. So now what has been done is, and MPEG is addressing these interchange formats, in particular addressing portable, dynamic and interactive 3D scenes. And so MPEG is for a long time developing core compression representation formats and the distribution and system integration of those. So the extension going now to 3D and XR is natural, and obviously there's a few aspects that had been already been developed, and we go a bit into this. So just as an organization, I don't want to spend a lot of time, but MPEG is distributed in different working groups, similar as other groups as well. led by technical requirements. And then you have groups that deal with video coding, audio coding, haptics and graphics. But there's also a systems group which looks into the integration of different medias into a full system environment. And basically groups that are in particular contributing this are listed here. So basically all of the main working groups contribute to representation formats for immersive scenes. And you will find here a list and a roadmap what's happening. I'm going to skip the details. You can digest it for yourself. It's also part of the MPEG webpage. But there is topics around media coding, such as audio and video, immersive video, mesh compression, point cloud compression. There are basically also tools that look at the integration and so on and so on. So it's just giving you an overview of many components being developed. And it's not only MPEG doing this, and it's basically all other organizations or proprietary technologies are developed that are basically addressing some of the aspects. So we take MPEG just as a placeholder, but what is looked at is the larger ecosystem. So now one of the questions is, how do we get from all of these different components that we have to dynamic scenes, right? And what I identified before, there's a collection of standards under the MPEG-I umbrella, which is MPEG immersive media. And you have different compression formats here, audio and haptics. There is optimizations to run and optimize multiple decoders in parallel, dynamic point clouds, immersive media, and so on and so on. So how can we create an integrated scene that basically allows to aggregate content, aggregate multiple objects, interact with the scene, update the scenes, and so on? And we studied different options, and MPEG has a history of having done already a scene description. And this study basically resulted then to look at what is the right format. And we basically took different aspects into account. Should we start from scratch, or should we use something existing? And here is a list of candidates, basically. And what is really of interest for what MPEG is doing, but also for the industry, is having a last mile distribution to consumer devices, where you basically reduce the complexity, you flatten the hierarchies, you're using compressed components for having using the network. It's basically adaptive to devices, to networks, and it basically supports features such as textures, light baking, and so on and so on. At the same time, obviously, if you go here, there might be in the exchange things that you do when you generate formats, very high fidelity, and so on and so on. So based on this, we basically said we're not going to be targeting and looking at the right end. We want to have a format closer to the left-hand side, and glTF is a good example for this one. At the same time, we understand that glTF, and that is a bit of a Wikipedia entry, is basically giving a lot of baseline functionalities already. It allows you to basically standardize, create three-dimensional scenes and models, and it's an open standard. And basically, it has many functionalities already that you would expect from a scene. So, and it's considered as this JPEG of 3D that's referred to here. So now the question was for us, can we use glTF and basically extend it in a way to address integration of real-time media, of aspects that you had been seen before, dynamic point clouds, dynamic meshes, but also 2D content, and so on and so on. And basically, that led to something that we said, let's combine the best of the two worlds, and let's use glTF as a baseline and use MPEG-I as basically the framework to integrate. And we basically synonymously said, let's create something like, and I apologize if you feel this is wrong, but an HTML5 for the XR and metaverse. And actually what HTML5 did, and there's a bit on the left-hand side you can basically do, but it extended HTML to something that basically integrates multimedia real-time elements directly. So there's a video plugin you can directly stream. It's very supportive to mobile. So it's basically simplified. It allows you to use environmental aspects being taken, geographical locations. You can reuse existing codecs on the platform. You also integrate a communication platform with WebSockets, WebRTC, and you add scripting. So we wanted to basically say, can we create a similar extension into glTF that supports this? And that is basically what MPEG-I scene description attempts to do. It's basically an HTML5 for 3D scenes, XR in the metaverse. And an important aspect is the synonymously also having an entry point document with a 3D experience is very important. So we don't want to defer this to an app or a Unity application. That is a possibility, but that limits the portability and interoperability. Having a document version is something that has been proven to be very, very flexibly being distributed. And then you can go to shared experience and basically integrate also networks and real-time media. So that was the initial ambition formulated in requirements. I'm very happy to say we completed the first version of MPEG scene description, and we created this by developing extension into Chronos glTF 2.0. And we worked heavily with the Chronos team to basically adopt this specification as extensions under the MPEG vendor extension framework, but very well defined and detailedly reviewed. And they have been added by Chronos on March 1st this year. And this is a great milestone, I believe, for MPEG, and I hope also for Chronos and glTF. What is in these extensions? That's what I'm going to hand over to Imed, who is the technical expert, and will explain you details of these extensions, how these requirements have been implemented. Imed.
Thank you, Thomas. Yeah, we can now we will now delve into the architecture first, and then we can look into the extensions that MPEG developed to glTF and in phase one, and the extensions that are currently being developed in what we call phase two. So on the architecture itself, the concept is slightly different to what we are used, at least in MPEG, with 2D media. So here we have like a central piece, which is the presentation engine. And if we can use the analogy to the HTML, as mentioned earlier by Thomas, that would be your browser. And the browser tries to consistently give you the same experience across different platforms, across different devices, and so on. And the entry point to that would be, in this case, the scene description document that gets loaded as the first thing, and that starts or indulges the user into this immersive experience. And the scene graph or the scene description comes over a separate interface, what we call the S interface. So that's where the presentation engine will fetch or acquire the first scene graph or scene description document, and then subsequently get the updates to the scene graph. So if we recall the use case we talked about earlier, where we have like a shared conference room space, users can come in and leave and stuff like that. So all of these will be updates that get loaded by every participant to reflect like the current status of that small world, basically, or shared space. So the presentation engine communicates with what we later get to know the media access function. It will through the media interface, it will tell it what media it needs, what different assets it needs to load, what are their components, and the description of how to access these components is provided in the scene description document. So that information gets passed to the media access function, which will load the media and so on. The other interfaces are like local interfaces and interactivity interfaces. So these are to provide the immersive interactive experience that we want to enable here. If we look at the more detailed like interface between the presentation engine and the media access function, which is the bulk of the specification that we refer to here, that was developed by MPEG. So you will not find that in the MPEG extensions registry in Chronos, actually. So this is documented in detail in the ISO specification 2390 part 14. So it defines this architecture, defines the interfaces, the APIs that we talk about here, like the media access function API and the buffer API. And the idea here is to really decouple like the media access from the presentation engine. So your presentation engine ideally should not have to worry about how your mesh was compressed or how that video texture was compressed, whether it's HEVC or AV1 or whatever. So it should not really be worried about these details. So the media access function will get the description of the media, its location, and it will try to find the best alternative coding or like access to that referenced media. It generates or it creates a pipeline that is tailored to that media format and will ensure that at the end, the raw media is passed to the presentation engine through a buffer interface. So it will store the decoded, decrypted media into a buffer that is well formatted. Its description is provided also in the scene description. So using all the like known features of glTF, like your accessors, your buffer views, and so on. And it will be clearly defined so the presentation engine can directly fetch the data and render it. The media access function API is actually has another role or plays another role in optimizing the media access. So media access, we have to keep in mind we're targeting like, if we keep this analogy to the web, you're targeting millions of devices, maybe billions of devices that have different capabilities, that have different access technologies to the network. Some are using Wi-Fi, others are using 5G and stuff like that. And you want to optimize basically the media delivery to these devices. So you want, for instance, to adapt if the network conditions change. You want to also to adapt the media to the current view of the scene. So if a user is located in one room and looking into a certain direction, then maybe the media access function can decide not to fetch parts of the scene that are not visible or are not expected to be visible. Or it can adjust, for instance, the level of detail of the media that it fetches. So all of that is enabled by the media access function API, which allows you to provide things like timing information, spatial information, media consumption information, and so on. So the media resources come with the scene description document, and we'll get to the extensions that enable that in a second. Then I said the media access function. So say you have a mesh, dynamic mesh, and it has one component that provides you with a dynamic texture, that means a video texture. So the media access function gets the request from the presentation engine to make that available. So it looks at the alternatives, it constructs what we call a media pipeline. So the media pipeline is dedicated to that access technology or the access description for that component. So say the video texture is accessible through Dash or HLS streaming. So it will construct a media pipeline that fetches the media using Dash, that decodes the media based on the used codec, does any necessary post-processing. For instance, it might need to convert from YUV to RGB if the buffer format expects it to be in RGB in a specific format, and then make it available in that buffer. Presentation engine only really cares about having that media in the buffer in the correct format at the correct time for rendering. So now we get into the actual extensions. So they are the key extensions are marked here in green, and the other extensions, the dependent extensions, are marked in gray. But these are the extensions that phase one of the MPEG scene description As defined, again, the goal was to add this dynamic, the time dimension, into GLTF. GLTF is currently only static, so this would add that dynamic aspect. It will add support for dynamic media like video textures, audio, dynamic meshes, and point clouds, and things like that. So that's the whole idea here. It all starts with the three extensions in green there. So you have MPEG media, which lists the access to the externally referenced media. You have an extension to the accessor to tell the parser or the presentation engine that this accessor will give you access not to a static buffer, but to a dynamic buffer, of which even sometimes the components, like the metadata, might change. For instance, the count might change from frame to frame. For a video texture, maybe that's not the case, but if you think about like a dynamic mesh, the number of vertices, the number of faces might even change from frame to frame. So you need a way to describe this dynamic metadata as part of the scene description document. That, in a sense, also leads into a buffer that is dynamic. So we call it buffer circular, like referencing the design of a circular buffer where you have simultaneous read and write operations. So the media access function would be writing into the buffer at the same time the presentation engine will be reading from it, and this simultaneous access has to be like regulated through this circular buffer. So if you look at the details of the MPEG media extension, so it has a description of the media, how to play it back, how it's accessed. So the access is provided through the alternatives, and you can have as many alternatives as you want. If you want to support like different encodings, different formats that you're in the devices that you're targeting, then you can provide multiple alternatives. The media access function would then have to be smart enough to pick the proper alternative based on its capabilities. So if it knows it has, for instance, accelerated decoding for a certain codec, it will pick the alternative that matches that like use that to construct a pipeline. So that's the whole idea here. So you can have describe different access. You can access dynamic streaming assets, like using Dash and CMAF. You can access real-time media using WebRTC. You can even access like locally stored content and media. And of course, the media access function will have to, in that pipeline, it will have to take care of any necessary processing like decryption, if the content happens to be encrypted, like post-processing if you need to convert from one format to a target format that is expected by the presentation engine. Then the buffer itself and the timed accessor. So the buffer itself, I said, is like a circular buffer. So it gives you like a description of like this extension will tell you that this buffer is circular. It allows like the buffer management then to create such a buffer with the recommended number of frames in the buffer, so to smoothly operate this media pipeline. So you don't get to lose frames because the buffer is or the write process is much faster than the read process, or vice versa, like run dry if the read process is much faster than the pipeline can feed the buffer. So that's the idea there. The timed accessors, I said, currently in glTF, you have like an accessor which points into a buffer view, which points into a buffer that is static. So what we added is the support for dynamic buffers, where you're able to even change some of the like accessor parameters. So you can have different configurations there depending on how you think or how the author thinks the data might change. So for instance, for a video texture, I know for sure that the width and height of the video will not change. Even if you're doing adaptive streaming, you do post-processing to produce like the same resolution of the video and then pass it in the buffer as a video texture. If you know that, then you can declare that all of these parameters are static, so no change, for instance, to the count, no change to the component type, and so on. So that's one configuration, but there are other cases where pretty much everything can be dynamic. Like if you're dealing with a point cloud, dynamic point cloud, then in one frame you might have 100K, and the next frame you can have 110K points. And you need to be able to describe these changes in the for every frame with every frame buffer. So that's what this dynamic accessor or timed accessor provides. In a sense, it gives you like the capability to provide an additional buffer view, which points into a section of the buffer that contains the dynamic parameters. So that's the whole idea there. But of course, that's optional just in case that you don't need it. Then you can just know that this is dynamic buffer with static parameters. And the parameters that can change are, again, like component type, buffer view, the type, whether it's normalized or not, the count, the min and max can change from frame to frame and so on. Same for the buffer view, the location of the buffer might change. You might be multiplexing multiple dynamic media into one buffer, which results in different byte offsets, byte lengths, and strides. So all of that is supported in these extensions. So you can have maximum flexibility for different use cases. The video textures is one of the first extensions that uses this concept. So it's an extension to a texture. Of course, if there is a fallback there, so if you don't support the video texture, then you can fall back to a regular image, a placeholder, so to say. But then the whole idea is that you have a pointer into an accessor that has the accessor timed extension. So that tells the parser that it needs to initiate this dynamic buffer for receiving the content. The next extension that was done was the spatial audio. So spatial audio allows for different types of sources. Actually, right now we support mono object-based sources and HOA. It allows for associating these sources with an effect. The effect that is currently in this version of the spec supported is the reverb effect, and you can add an audio listener that tracks basically the user. So it's recommended that the audio listener is either a child node of the camera of the scene or is an extension to the camera. So that keeps track of the movements of the user and makes sure that the audio is binauralized properly based on the current pose and position of the listener. And of course, we're looking in phase 2, we're looking at more advanced audio support, which I'll talk a bit about later. There are some other extensions, like an extension to point into a stream that gives you scene updates. So that can be built into the scene description document. So the glTF file basically would tell you you will be getting updates through this channel, and it can point into an access channel for that. You can have recommended viewports just in case you're consuming this in a 2D device, not in an AR or XR, VR type of environment. Then you can have recommendation of how the author recommends how to see the content. Also an extension for animation timing, so you can provide instructions on how to operate the animation in a dynamic fashion, so to say. Now is the time to show a quick demo. So we have implemented this in reference software in MPEG as part of the standards activity, but at the same time we are working on open sourcing a Unity player implementation of this. I'll show the implementation, and I think this should be available. I'll provide a link later, but it should be available really shortly, like hopefully in July, still like by end of the month. So let me just share my whole screen so that I can show the demo quickly, and hopefully you'll be able to also hear the audio. But it's like a player, a Unity app that is able to load in the runtime, the glTF, the MPEG scene description actually. So glTF with the extensions and play it back. So I gave it like the glTF file I want to play here. It takes some time to load, but hopefully it should show up soon, and hopefully you can hear it. I'll stop here and get back to the presentation. So basically what we saw there is really quite simple, but the idea is that you can provide these documents authored in MPEG scene description into a player, and you can like load it at runtime and render it. So that's the whole idea. At the same time, we're working on the authoring side of it. So we're working on Blender implementation of these extensions, so you can author and export scenes in MPEG scene description and use a player like this to render them. So that's the idea there, and we are committed to making these projects like open to the public, so as open source. So that's what we're planning to do. So now is probably the time to look into the more exciting extensions, what we call phase 2, which will round the experience by addressing like different features to close the gap, basically. Here, I would like to thank, of course, my colleagues from InterDigital for providing some of the content here. So the extensions in phase 2 are done to add support for AR, for interactivity, for dynamic lighting, for avatars, and for haptics. And hopefully also we managed to add support for more 6DoF, more immersive audio. And I'll talk to that in a bit. So for AR anchoring, the idea is that, of course, that app there works quite nicely in XR. If you put on your Oculus device, for instance, you'll be able to see the scene. You can just walk around, but the experience is missing. Like you might want to do that in an AR environment, so you want to anchor the scene to your real world and see it in a more like familiar environment, your room or whatever, your office or things like that. So the idea there is to enable like in the scene description itself to tell the receiver that there are few trackables. This is where you can track the scene or parts of the scene, like some root nodes of the scene too. And if the receiver has the capabilities to do AR, they will be able to do that. So they will identify these trackables. So there are reference trackables like floor or things like that, but you can also provide like application specific trackables like an image or a QR code or things like that. And then it tells you how to anchor your scene to that. Like, do you need to scale it? Do you need to rotate it or transform it in a way to fit in that environment. So that's what this extension is doing. The next extension is on interactivity. So this is the simple interactivity mechanism that works based on behaviors that bind triggers and actions. So you have triggers, which could be like collision or proximity or some user input or visibility of some object. And actions would be like activating something, transforming something, blocking the camera motion, animation, starting some animation, playback of media, manipulating some parts of the scene, changing some material, and activating some haptics output. The next extension we're working on is how to integrate avatars. And really, avatars, if you think about it, they are just meshes, probably. Maybe dynamic meshes or animated meshes. But I think the key differentiator here is really that you're able to interact with these avatars. So avatar is supposed to be your digital twin. So you can use your hands, for instance, to interact with the scene, like turn on the TV by touching the remote or opening the door or light switch or things like that. So that's the idea. So we want to describe the avatar and also in a segmented way so that you know, for instance, these are the hands, and you can associate interactivity with these segments of the body. Like the hands or the fingers, you can associate, for instance, a proximity or a collision trigger with them to activate certain actions. So that's the whole idea there with the avatars. But at the same time, we're also defining like a reference avatar, Morgan, what we call Morgan. So it's a reference avatar that comes in 3 different levels of detail that can be used, if people want, of course, for their scenes. Dynamic lighting is another extension that we're developing, or set of extensions. So it allows you to add image-based lighting that is dynamic. So it's more like a video in a sense, or where the coefficients can change over time, like the reflectance coefficients can change dynamically. Say if you're capturing your light environment and you're using that for AR anchoring of a scene, and you want to create like realistic shading and stuff like that. So you would need to track the current light environment or light map and use that to perform your rendering. And finally, haptics is another extension that allows us to support rich haptics experience with a wide range of like haptics, actions or haptics like features like stiffness, friction, temperature, and so on. Of course, hopefully devices that support all of these different haptics features will be available in the market, but we have support for them, so you can trigger different actions. Say if you run your hand by a wall, depending on the texture of that wall, you will have like a haptics experience, hopefully, that reflects the structure of the wall, if it's smooth or not, for instance, and so on. So support for haptics is also integrated in this phase 2 into scene description. I talked about richer audio, so I think what we're trying to do there is to integrate MPEG-I audio or 6DoF audio solution. So that's a more advanced audio support than what we have with spatial audio. So it includes things like acoustic materials and so on. Like it should provide like with a more accurate. It's more like PBR basically for audio. So that's something we're also working on together with the audio group in MPEG. So finally, I'd like to point into these references. So we have the Chronos extensions can be found under that link. We have a GitHub repo where hopefully people can, even the public can like provide us with feedback. So about like issues or like other like requirements or feature requests or things like that, that we can feed into the standards process. So we want this to be open to the community, to the public actually. So not just limited to the MPEG community. And we want to hear your feedback basically. We also published a white paper that is open and can be accessed if you want to read more details about this. And the reference software will be available as part of the 5G NAG project. And the Unity player, one of these projects should be available hopefully this or next week in that repository. And with that, I conclude my part and look into getting some questions.
Thank you, Imed. That was great. Now we'll open the floor to the Q&A portion of the webinar. So please feel free to submit any questions you have by using the Q&A feature on your Zoom toolbar. And we'll get started here. Thomas, how is the coordination between MPEG and Kronos working so far, and what will come next?
Jeff, yeah. So first of all, I would like to thank the colleagues from Kronos, because obviously we have been stressing them a bit by developing full extensions which were carefully reviewed by the MPEG process, which includes reviews by the national body, basically the whole world. But then we submitted this into the Kronos repository, which is a GitHub-based pull request. And the colleagues there, especially Alexei, the editor, spent quite some time of reviewing this and then giving us detailed feedback and comments that improved this significantly. So on this working level, it was great. Also, the process with having the ability to extend, I believe that's a great functionality given by Kronos. And so we believe this is exemplary, so much appreciated. And looking forward, we try to basically provide more extensions. At the same time, we want to be very careful that there is not overlapping work being done in Kronos and in MPEG. So a coordination also ahead of time is continuously needed, and we're trying to do this. One of this is this webinar, but also on working level, we continue to exchange information. But it's great to have this collaboration, and it lives with the people there. So I would like to thank the people in Kronos, and specifically the 3D working group, to being so supportive.
Awesome. This comes in from Harry. He asked, is there or will there be a browser-based reference implementation?
Yes, thank you. I forgot to mention that, Thomas. I can take this. Actually, that's something that we're doing right now. So we're implementing this as part of 3JS or as an extension to 3JS. And we also plan to make that open source in the near future. That said, I think I was made aware that there is another project that is out there on GitHub that is implementing this as well for the web.
Excellent. Helmut asks, in the future, much of AR, VR, and video calls will be based on generative machine learning models like GANs. Will these be considered to be part of this framework?
Well, I take it first, but then I defer to Imed. I mean, we're discussing this continuously, which is internally also with, there's a lot of opportunities with generative AI, ML, obviously, and that will probably change and revolutionize some of the aspects. At the same time, it's just believed that more content will be available that can be distributed and shared. And we will obviously look into this. I believe the framework is there, but Imed might have more on the technical details. So yes, I would say yes, very interesting. Technical details probably need to evaluate, but Imed.
Yeah, so AI is of course present there, and generative AI is very important. So for AI itself, I think when we look at the avatar, so we're taking into account existing approaches that animate your avatar mesh using AI. So you can use AI to detect the body pose, to detect the facial expressions, and animate your avatar. And that's type of thing can be integrated into scene description and is actually integrated as part of this avatar. So you can provide also access to streams that contain like neural codes or weights to animate your avatar that are produced by AI. Generative AI is even more. I think like it's on the longer run. I think that will have like great impact. So we're looking into things like NERF, where you don't have to generate a mesh. You can directly, based on the camera pose and stuff, render the mesh, and how that can be composited with the rest of the scene. I think that's all things that we are looking into and tracking in the scientific community and the industry.
Imed, when can we expect the source code of the Unity player to be made available to the public?
Yeah, thanks, Jeff. I think that try to answer that in my talk. So that's something that we have been pursuing, and I know we promised that, for instance, to Kronos last month, but has been delayed a bit due to some procedures. But I think we are very close to making it available. So hopefully in the next week or two at most, this should be accessible, and hopefully people can get their hands on some test sets. Of course, maybe the one I've shown, and they can start using it and give us also feedback how we can improve the technology we have there. Thank you.
Okay. And you also referenced an open source Unity player, but are you planning to provide some open source content generation tools to support the MPEG Scene1 description extensions?
Right. So we have another project on extending Blender to support export into MPEG scene descriptions, or glTF with the MPEG extensions, and hopefully that should be made as an open source project soon as well.
So Thomas, how do the standards created in MPEG and Kronos relate to your Qualcomm products? Can you provide some insight into that?
Yeah, I think that's good to relate a bit to what we do in Qualcomm. Obviously, we are very centric to device hardware, but as we have elaborated before, device hardware for XR is very much stressed by significant constraints. So we basically need to put aspects such as decoding, rendering in hardware to be very power efficient, to be creating an excellent experience. So we also need to make sure that there's not a huge fragmentation of technology. So that's where standards come into play. And Kronos and MPEG are core standards to support rendering, to support device APIs for XR, OpenXR, Kronos, glTF, the graphics APIs, and MPEG to define compression standards that are also very centric to hardware. And so this has significant impact. glTF and MPEG scene description on top of this should expose these existing hardware functionalities in a simpler way to app developers. So basically, by creating content within the format, you get access to our hardware without having to write specific apps and understanding potentially all of the detailed APIs interface that go down into the hardware. So that's the benefit basically of the standards, that we really can expose the complex hardware functionalities simpler to the app developers.
And Thomas, I know you're very heavily involved in the Metaverse Standards Forum. How does the work of the MPEG relate to the activities there?
Yeah, I mean, MPEG and Kronos work on glTF. There is a group that actually looks into some aspects related to glTF interoperability with authoring formats. But I believe there's an understanding that we need to have a distribution format that is flat, that is easily accessible, that is widely supported, and glTF is that format. The same is basically formats defined by MPEG. Video codecs, decoders, audio codecs are well known from the MPEG community and are supported on a lot of hardware. So basically, creating this interoperability from authoring to distribution is a core work item in the Metaverse Standards Forum, very related. Then generally going into the Metaverse, we believe that it's going to be, the Metaverse is something like, has many aspects of what the web has. And the web lives from the simplicity of being running on browsers, being very portable. So something similar being available for the web is obviously something that is expected to be needed. And this contributions from glTF with the extensions is probably a component that supports the Metaverse. And there's probably other aspects that come into play, but at least a few of those that relates this very closely to the Metaverse aspects, and specifically also to the standardization aspects dealt in the forum.
Great. Thomas, Imed, thank you for the discussion today. We truly appreciate your time and effort in putting together today's meetup. As a reminder, a recording of this presentation along with the slide will be available on the Kronos Group website, and a direct link will be sent to you in a follow-up email. As you leave the webinar, please take a moment to fill out the survey that pops up. Your feedback is important to us to help us improve these presentations. Please let us know if there are other Kronos-related topics you may be interested in. And thank you for joining us, and have a great day.
Thank you very much.
Thank you. Bye-bye.